This is CFD from Scratch. We're still discussing the finite volume formulation of the method. In the first video we talked about the governing equations. In the second video we discussed some aspects of pressure. In the previous third video we talked about the finite volume formulation, and we're continuing that discussion now. So before we set up the grid and talked about the need for staggering the grid to avoid pressure checkerboarding. And then we looked at the momentum equations, both the U momentum and the V momentum. And now in this video we're going to look at the solution of the pressure equation, or developing the pressure equation from the mass balance. We discussed that generically in a differential form in the second video. And so here we're going to follow up with that in terms of our discretized form of the equations that will put us in a place where we're ready to code them up. Okay, so we begin with the continuity equation. We integrated the U momentum equation over the U grid, the V momentum equation over the V grid. For the continuity equation, the mass balance is integrated over the P grid. And we can go back and just have a quick look at those grids. So we have a P grid, a U grid, and a V grid, and we integrate U momentum over the blue cells, V momentum over the red cells, and we'll integrate the mass balance over the black cells. And this is what these grids look like when they're overlapped. Okay, so for the mass balance, this is an area integral. And we have the integral of v dot n dA over the area, and we can split this into an integral over each face. So we'll have v dot n dA over the east face plus the west face plus the north face plus the south face. And then the east face, n is I, west face it's minus I, north face it's j, south face it's minus j. So when doing that, v dot I will be u, and v dot j will be v, non-vector v, and then dA is either delta x or delta y. So we end up with four terms, 1, 2, 3, 4 terms, with 2 negative signs and 2 plus signs representing those faces. Now, with respect to the grid quantities, east is ui plus 1j, west is uij, north is vij plus 1, and south is vij. And so if we insert these into the discrete finite volume equation for mass, we end up with this equation here. Now, in order to derive a pressure equation, we're going to take our momentum equations for the velocities, and those momentum equations for velocities are written in terms of pressure. So if we insert them into this equation, then this equation will end up being a pressure equation. So we do that as follows. The U momentum equation is given by the following: du dt equals big H minus delta P over delta x. And we have a similar equation for the V momentum equation, and then we're going to apply a simple, we're going to integrate this equation in time using a simple explicit Euler method. So explicit Euler will say delta U over delta T equals the right-hand side. And the delta U is really, so then we multiply the dt across, and then this delta U is U minus U. So we have to put the U across. So if you pull the U over, it's delta U, and if you divide by delta T, it's delta U, delta T equals the right-hand side. Here we're using delta T is H, so H is our time step size. And then we have these U and V momentum equations applied to the specific grid points that we need. I plus 1, Ui plus 1j, Uij, Vij plus 1, and Vij are given here. So these correspond directly to these quantities. So then we're going to take those four discrete momentum equations, time advanced momentum equations, and literally insert them directly into this equation. So we'll take all of these right-hand sides and insert them into that mass equation, and the result will be a single equation. You'll have this whole equation times delta y minus this whole equation times delta y plus this times delta x minus this times delta y all equals 0. And the result is an equation for the pressures. So when we make that substitution, substituting those into the continuity equation, we're going to group the terms. So all the pressures we're going to put on the left-hand side of the equation, and all the other terms we're going to put on the right-hand side of the equation. And we're going to arrange this so that we have Pij minus 1 plus Pi plus 1j plus Pij plus Pi plus 1j plus Pij plus 1. So if we go back to our grid, our P grid here, for a given cell, we have neighbors up and down, north and south, and we have neighbors east and west. So we're going to have Pij minus 1, Pi minus 1j, Pij, Pi plus 1j, and Pij plus 1. And that's what these terms are. The lower, the left, the middle, the right, and the top. Okay, now we've also labeled these terms to indicate where they come from. So and this doesn't mean that this term is V south. It means that this term came from V south. And likewise, this term came from V south. And that's convenient when we look at the different kinds of equations here, because the equation listed here is an interior cell and all of the neighbors are present. But we really have 9 different kinds of cells. We have the interior cells, then we have 4 different corner cells, and we have 4 different edge type cells. So this notation, CBL, means corner bottom left, EB means edge bottom, edge left, edge top, edge right, corner top right, etc. Now, in writing these equations, if we're on a corner, suppose we're on this corner bottom left, then in the bottom left corner, when writing the momentum equation, the bottom left corner doesn't have, in the bottom left corner, u west is the actual boundary velocity, and v south is the actual boundary velocity. So we're going to do a lid-driven cavity, which means that we know the velocities on all of the boundaries of our domain. And that means that if we're on a boundary where we know the velocity, then we don't substitute the momentum equation in for this term. We simply use the known velocity. And that means that in our equation, some of these coefficients will be 0. Like there's no coefficient of p, so this, if we're on that bottom left corner, this coefficient will be 0 because there's no west pressure. And likewise for this coefficient of p, because there's no, not that one, this coefficient of p, because there's no south pressure. So in that bottom left corner, these 2 coefficients are 0 because we're on the edge. And similarly, this v south, we don't use this term. We use delta x times v south, where v south is just known. And on the west, similarly, we use delta y times the known u west quantity. So this, these brackets kind of help us to know how to change this equation for the different types of cells that we have, because we're going to need to write all 9 versions of this equation for each type of cell, and then we'll need to code those. Okay, so as we do that, let's summarize here. We have a p equation for each type of cell, and the equations differ in which velocity making up the equation is on a boundary face. For a cell with a velocity on a face, like an edge top cell, the coefficient of Pij plus 1 is 0, the second term of the coefficient is decreased by from factor 2 to factor 1, and the corresponding term on the right-hand side of the p equation is replaced with the known face value. So that was kind of what we discussed previously, but we noted that this term, if we're on like a top edge, for example, then v north, this whole quantity will be replaced by v north, well, delta x times v north. And we won't have a north coefficient, and because this Pij term includes a component that came from v north, this 2 will become a 1. So in corner cells, we lose 2 of these coefficients, bottom left corner, top right corner, and we also decrease these, we delete these 2's. On edge cells, we delete only 1 of the 2's and only 1 of these coefficients. And so that's kind of the pattern, and you can work through what that is. Now, I've written a little table here to help illustrate that. So this table, for each of the type of cells, interior, corner, edge, edge, corner, these quantities are the coefficients that multiply this these p values. The p values are what we're solving for, and what we have is an algebraic system of equations. So we're going to end up with an ax equals b system, where in this case x is p, so an AP equals b system of equations. And so we're going to have to set up that matrix of coefficients of p, and this table will help us to set that up by knowing what the values are of the coefficients. And this table applies for if we're an interior cell, for example, then these coefficients are what we would use for every interior cell, and every interior cell has a base pressure and 4 neighboring pressures. So we could say that we have a matrix of base coefficients, a matrix of, and when I say matrix, I mean 1 for each value of our grid. Every point in the grid has a base pressure and 4 neighboring pressures. And we'll use those to construct a matrix for the linear system, but we'll look at the details of how to do that later. Now that was for the p coefficients, this left-hand side of the equation. The right-hand side of the equation is the b part of this AP equals b system. And so similarly, this b array will have different values depending on whether we are one of these 9 cell types. And that's listed in the following table. So here, unlike the previous, these aren't coefficients of b, this is just the additive terms. So for interior cells, this is the this quantity, the whole sum, is the value of b for an IJ cell that's an interior. When we're on other cells, we have exactly the same thing, except some of the terms are changed depending on what edge you're touching. So if we're a corner bottom left, then this term becomes delta x v south, and this term becomes delta y u west. But the other two terms are the same as they were above, and so forth for the other equations. So these 2 tables are convenient when we want to go and code the resulting system of equations so that we can actually solve the method. Okay, so that's as far as we'll go, and in the next video we'll look at taking these equations and implementing them in Python for a lid-driven cavity problem.